If you buy a $10,000 NVIDIA A100 GPU to train your next massive AI model, you might be shocked to learn a dirty little secret about how it actually runs.
Oh, yeah. It's honestly a bit tragic.
Right. Because those incredibly powerful compute cores, like the silicon that you paid top dollar for, they spend a huge amount of their time doing absolutely nothing.
Nothing at all, just sitting there.
Exactly. They're
Oh,
completely starved for data, just waiting on this microscopic traffic jam.
It's really the ultimate irony of modern artificial intelligence, you know? I mean, we build these breathtakingly fast processors, and then we bottleneck them by making them wait for the data to physically travel across the circuit board.
Welcome to the deep dive. We've got a great kind of late night session lined up for you tonight.
Yeah, we do.
If you're tuning in, you're likely a fellow software engineer looking to level up your AI knowledge, and well, you are in exactly the right place.
Grab a coffee or, pull up a terminal window.
For sure.
Yeah.
Because tonight's mission is all about a breakthrough called flash attention.
And just to set the stakes right out of the gate here, flash attention is like the specific algorithmic breakthrough that made modern transformers remarkably faster.
It's huge.
Yeah. If you've been wondering how these massive large language models are suddenly able to process huge context windows,
Like reading entire books?
right, or parsing massive code bases without just grinding to a complete halt, this is the exact mechanism that made it physically possible.
It's just a fantastic story of engineering. We're pulling from a stack of source materials tonight that break down the underlying mechanics of self-attention, the physical memory architecture of a GPU, and a really brilliant paradigm-shifting optimization by a researcher named Tri Dow.
Yeah, his work is incredible. But, before we get to his elegant solution, we kind of have to look at the car crash he was trying to clean up.
Yeah, we really need to understand what was slowing everything down in the first place.
Because you really can't appreciate the genius of the fix until you feel the pain of the problem.
This is true.
And to feel that pain, we have to revisit the core mechanism of the transformer architecture itself, which is the self-attention mechanism.
Right, and in previous deep dives, we've talked about the high-level idea of self-attention. The fundamental rule there is that every single token in a sequence must communicate with every single other token.
Right.
But mechanically, how does that actually happen, like under the hood? Our sources break this down into 3 specific matrices that the algorithm computes for a sequence of n tokens.
The famous Q, K, and V.
Exactly. Queries, keys, and values. Let's unpack what these actually represent in the code.
Well, the best way to think about Q, K, and V is like a database retrieval process, but fuzzy and mathematical.
Fuzzy database. I like that.
Yeah. So the query is what a specific token is looking for. The key is like the label or the description of what another token contains.
Okay.
And the value is the actual underlying meaning, the payload of that token.
So if my sequence is the sentence, the bank of the river, and I'm looking at the token bank, its query is essentially broadcasting like, I am a noun, I could be financial or geographical, who around here has context?
Precisely. And the token river has a key that says, I am a body of water.
Got it.
So to figure out if there is a match, the algorithm takes the dot product of the query vector for bank and the key vector for river.
And the dot product, mathematically, just acts as a similarity metric.
Yeah, exactly. A high dot product means the vectors are pointing in roughly the same direction in this high-dimensional space.
Meaning there's a strong relevance.
Right. And a low dot product means they're unrelated. So you compute these dot products for every single pair of tokens, and that creates your attention scores. Finally, you multiply those scores by the value vectors to get the final contextualized representation of the word.
I like to visualize this early step, matching the queries and the keys as a massive networking event.
Oh, that's a good way to look at it.
Right. Let's say you're hosting a small local tech meetup. You have 10 people in a room. And the strict rule of this event is that every single person must introduce themselves and shake hands with every other person to see if they should collaborate.
With 10 people, that's trivial. Everyone shakes hands, connections are made, and the context of the room is established in 5 minutes.
But now, scale that up.
Yeah.
Imagine you rent out a massive convention center and you invite 10,000 software engineers.
Oh, boy.
And the rule is exactly the same, right?
Yeah.
Every single person must find and shake hands with every single other person in that building. You don't just have 10,000 handshakes.
No, you have an exponential explosion of connections. Every single person is seeking out 9,999 other people.
Exactly. It's chaos.
And mathematically, that is exactly what the self-attention mechanism requires. It results in an n-by-n matrix of interactions.
An n-squared grid.
Yeah, if you have n tokens, you are generating an n-squared grid of dot products.
So what does this n-squared reality mean for a software engineer trying to build a bigger model? Because let's be real, big O of n-squared is basically a swear word in our industry.
It really is. And it means you are fighting a brutal, losing battle against scale.
How so?
Well, if you double the length of the text you feed into the model, you don't double the computational work, you quadruple it.
Wow.
Yeah. If you want a model to process 100,000 tokens instead of 1,000, the size of that n-by-n matrix becomes astronomically large.
It just balloons.
It becomes a massive computational roadblock that historically forced researchers to keep their input sequences painfully short.
And for a long time, the assumption was just, well, that's the math, you know.
Right.
The formula requires every token to check against every token, so we just have to bite the bullet, allocate more compute, and wait for the math to finish.
But our sources highlight a massive twist here.
Yes, they do.
The bottleneck isn't actually just the sheer number of mathematical operations. It's the physical room where the math is happening. We have to pivot from the abstract software matrix to the physical silicon.
Which is such a crazy shift.
It is the crucial shift in perspective.
Yeah.
To truly understand why flash attention is such a big deal, you have to stop looking at the Python code and start looking at the physical environment of a modern GPU.
Specifically, the memory hierarchy of an NVIDIA A100.
Exactly.
Now, hold on. Let me push back on this for a second.
Sure.
Because as a software engineer listening to this, my day-to-day life is living in the abstraction of big O time complexity. I'm looking at algorithmic efficiency. I assume memory access is mostly big O of 1, constant time.
Right, of course.
And when I do worry about memory access, I generally assume the hardware has my back.
Yeah.
Modern CPUs have L1, L2, and L3 caches specifically designed to prevent memory delays.
Yep.
So why are we suddenly dropping down into the basement to manually inspect the physical memory hierarchy of an A100? Doesn't the hardware cache handle this n-by-n matrix for us?
That is a brilliant pushback, and it hits on, honestly, the great lie of modern computer science.
The great lie.
Yeah, we are taught to assume that memory access is big O of 1, but that assumption completely falls apart at the bleeding edge of hardware.
Interesting.
The caches you're talking about work beautifully for normal, predictable workloads, but an n-squared attention matrix completely blows out standard hardware caches.
It's just too big.
The matrix is simply too massive, yeah.
So what you're saying is that this isn't a compute-bound problem at all. It's entirely an I/O-bound problem.
Absolutely. I mean, the compute cores on an A100 are capable of over 300 teraflops. They are unfathomably fast.
Okay.
But to understand the I/O problem, you need to look at the two types of memory on that GPU.
Let's hear it.
First, you have the high bandwidth memory, or HBM. This is the main warehouse. On an A100, it might be 40 or 80 gigabytes.
That's a decent amount of space.
It's huge, but relatively speaking, it's physically far away from the compute cores, and it is slow to access.
Got it. And the second type?
Right next to the actual processing units, physically on the same piece of silicon, is the SRAM, static random access memory.
And I'm guessing that one is fast.
SRAM is blisteringly fast. It operates at the speed of the computation itself. And here's the kicker, because it is so physically close, and because of how it's manufactured, it is highly constrained.
How constrained are we talking?
You might only have around 20 megabytes of SRAM per streaming multiprocessor.
Wait, really? 20 megabytes?
Oh.
So it's 20 megabytes of ultra-fast workbench compared to 80 gigabytes of slow warehouse storage.
Exactly. Now think about your n-by-n matrix of attention scores. As your sequence gets longer, that matrix gets massive. It cannot possibly fit on that tiny 20 megabyte SRAM workbench.
Oh, I see. So it has to live in the large, slow HBM warehouse.
Yes. But the GPU cannot execute the math out in the warehouse. The processors only work with what is on their local SRAM workbench.
So they're constantly shuffling data.
Right. To compute the attention, the GPU has to constantly ferry huge chunks of that massive n-by-n matrix back and forth.
Sounds terrible.
It is. It reads a chunk from HBM, moves it to SRAM, does a tiny bit of math, writes the intermediate result back out to the slow HBM, and grabs the next chunk.
So the read and write operations are killing us.
Exactly.
The software engineer is staring at their terminal, cursing the matrix multiplication math, when in reality the math itself is finishing in a fraction of a millisecond.
It's basically instant.
It's the physical transit of the data across the microscopic real estate of the circuit board that is causing the delay.
Mm.
The processor's just sitting there waiting for the memory bus.
You are hitting what hardware engineers call the memory wall. You can make the processors as fast as you want, but if you can't feed them data fast enough from memory, the whole system stalls.
Wow.
The physical data transfer of the intermediate n-by-n matrix is what actually chokes the hardware.
Okay, this completely changes the framing of the problem.
Yeah, it does.
Because if the massive n-by-n matrix is choking the hardware because it takes too long to ferry the intermediate steps back and forth from the slow HBM, then the ambitious engineering question isn't like, how do we do the math faster?
Right.
The question is, how do we stop ferrying the data?
Or, even more radically, how do we bypass building that massive intermediate matrix in the HBM altogether?
And that brings us to the breakthrough moment. This is where the source material introduces Tri-Dow and his incredibly elegant algorithmic solution.
Yeah, Tri-Dow looked at this memory wall and had a completely paradigm-shifting insight. He asked, what if we never actually materialize that full, massive n-by-n intermediate matrix at all?
But wait, if self-attention mathematically requires computing the dot product of every query against every key, how could you just, not build the matrix that records all of those scores?
This is where Tri-Dow introduced the concept of tiling. He redesigned the algorithm to compute the attention in self-contained blocks or tiles.
Okay, I want to use an analogy here because understanding the mechanism of tiling is so crucial for this.
Go for it.
Let's imagine you're a chef in a tiny, cramped kitchen. You have been tasked with making a massive, 10,000-serving batch of a very complex soup.
Okay, sounds stressful.
Right. Your raw ingredients are stored in a massive walk-in freezer down the hall. That freezer is our slow HBM memory.
Got it.
And your only workspace is a tiny cutting board right next to the stove. That cutting board is our ultra-fast SRAM.
This is a really great way to visualize the constraint.
So the traditional naive approach, the standard attention implementation, is like walking to the freezer, grabbing one onion, walking back to the cutting board, chopping it, walking the chopped onion back to the freezer to store it, and grabbing the next vegetable.
So much walking.
You're constantly moving intermediate ingredients back and forth. You spend like 90% of your time walking down the hall and 10% of your time actually cooking.
It's exhausting, and the kitchen grinds to a halt.
Right. So the tiling strategy completely rewrites the recipe to respect the size of the cutting board.
Oh, nice.
Instead of constantly moving intermediate chopped veggies back to the freezer, you grab a specific small batch of ingredients, a tile. You bring them to the cutting board, you chop them, process them, and crucially, you throw them immediately into the boiling pot on the stove to accumulate into the final soup.
Yes.
And once they're in the pot, you wipe the cutting board completely clean for the next batch. You never store intermediate ingredients in the freezer.
The key word you just used there is accumulate.
Accumulate.
Right. By processing the math in these small self-contained blocks, these tiles, and keeping a running accumulation of the final output matrix right there in the fast SRAM, you drastically reduce the number of times the GPU has to read and write to the slow HBM memory.
And you're not changing the final output at all. The soup taste is exactly the same.
Right.
The mathematical result of the attention mechanism is identical. You have just completely redesigned the workflow to avoid the memory bottleneck.
And that is exactly why flash attention is such a celebrated piece of engineering. It is a masterclass in hardware-aware algorithm design.
It really is.
Tri-Dow didn't just accept the abstract math at face value, you know. He looked at the physical constraints of the SRAM. He changed the loop structure of the algorithm itself to minimize memory reads and writes.
Amazing.
By keeping the operations local to the fast memory, flash attention made the processing of long sequences wildly faster.
It's an architectural intervention. It proves that code doesn't execute in a vacuum. It executes on silicon. And the layout of that silicon really matters.
It absolutely does.
So problem solved. We chop the matrices into tiles, process them on the fast SRAM, keep a running sum, and we can certainly feed entire books into our language models.
If only computer science were that accommodating.
Ah, right. There's always a catch.
As always, there is a catch. Tiling brilliantly solves the physical memory bottleneck, but in doing so, it immediately breaks the strict mathematics of the transformer.
Okay, let's get into the weeds on this, because this is the dramatic engineering cliffhanger of our sources today.
It really is.
We have this beautiful tension between the tiling solution we just outlined and the rigid mathematical requirements of how a transformer actually calculates attention. What part of the math breaks?
It comes down to a specific operation called softmax.
Softmax.
Yeah.
Yeah, this is everywhere in machine learning. Mechanically, it's a normalization function, right?
Correct.
It takes a bunch of raw numbers, in our case, the raw dot product scores,
Yeah.
between the queries and keys, and turns them into a nice clean set of probabilities that add up to exactly 1 or 100%.
Correct. But we need to look at exactly how softmax does that, because the formula for softmax involves taking the mathematical exponential of every raw score.
Oh, I see.
It raises the mathematical constant e to the power of the raw score.
So e to the x.
Exactly. And here is where the mechanical reality of software rears its head. Exponentials grow aggressively fast.
They really do.
If your raw dot product score is a relatively small number, like 10, e to the 10 is roughly 22,000, that's fine.
Totally manageable.
But if your raw score is 100, e to the 100 is an astronomically massive number with over 40 zeros.
Oh, I see where this is going.
Yeah.
Standard floating point architectures cannot handle numbers that large.
Not at all.
The hardware just throws its hands up.
You get a floating point overflow. The computer spits out nan, not a number. Yeah. The entire calculation crashes because the values are just too large for the physical memory registers to represent. This is a classic problem in numerical stability.
So how is softmax normally calculated without crashing the whole system? Because standard attention obviously uses softmax.
Right? There's a standard mathematical trick. Before you exponentiate the raw scores, you scan the entire row of numbers, find the absolute maximum value, and you subtract that maximum value from every single number in the row.
Okay, let me make sure I'm following the math here.
Sure.
By subtracting the maximum value, the highest number in your row becomes 0, because max minus max is 0. And e to the 0 is just 1. All the other numbers in the row become negative numbers, and the exponential of a negative number is a small fraction between 0 and 1.
Exactly. It completely prevents the floating point overflow. The math remains identical in terms of proportions, but your numbers stay perfectly safe and small.
That's a clever trick.
It is. But here is the critical catch detailed in our sources.
Okay.
To perform this standard mandatory trick, you mathematically require knowing the true maximum value across the entire row of the matrix.
Wait, you see it.
Let me put my debugging hat on.
Yeah, put it on.
The softmax formula needs the maximum value of the entire row to prevent crashing. But we just spent the last 10 minutes establishing that our entire hardware strategy tiling specifically avoids loading the entire row.
Exactly.
We're only looking at a tiny tile of the matrix on our fast SRAM cutting board. If I only have a small chunk of the row loaded into local memory, how can I possibly know what the true maximum value for the whole row is?
You can't.
The highest number might be in a tile that is still sitting in the slow HBM freezer.
It is a massive contradiction.
Doesn't this softmax requirement completely defeat the purpose of tiling then?
That's the problem.
If softmax forces us to scan the entire row to find the maximum value before it can safely compute the probabilities, then we have to go right back to loading the entire row in a memory, which puts us right back at the memory wall.
That is intensely frustrating.
Yeah.
You're caught in a trap. On one side, you have brilliantly solved the physical hardware bottleneck. You chunked the data, you respected the SRAM, and you eliminated the I/O transit delays.
We were so close.
But on the other side, the pure math is demanding that you zoom out. The softmax formula is stubbornly demanding the whole picture before it can proceed safely.
So you are caught between the physical reality of the GPU and the abstract rigor of the formula.
Exactly. If you obey the math and load the whole row, your hardware stalls on memory transfers. If you obey the hardware and only load a tile, your softmax operation overflows with exponentials and crashes with NaN errors.
So this beautiful, elegant tiling concept is fundamentally at odds with the very mechanism that makes the AI work.
And that is the cliffhanger our sources leave us with.
Man.
The sheer existence of flash attention, though, proves that Tridow figured out a way to square this circle.
He must have.
He figured out the mathematical gymnastics required to calculate a global maximum while only ever having local visibility of a single tile at a time. It requires keeping track of running maximums and dynamically updating the running sums on the fly.
It's an incredible place to pause and process, because the progression of this problem is just so fascinating.
It really is.
It really highlights how deep you have to go when you're pushing the limits of computation.
It's a masterclass in full-stack systems-level thinking.
It really is. We started high up in the clouds with pure abstract math. We looked at self-attention and how every token generating a query, key, and value creates an O of n squared explosion of dot products.
Right.
We saw how that scaling creates a nightmare for processing long sequences. Then we dropped down to the metal. We zoomed all the way in to the physical architecture of an NVIDIA A100.
Down to the silicon.
Yeah, and we realized that the massive big O lie, the assumption of constant memory access, was hiding the real bottleneck, which was the physical transit of data back and forth from the slow 80 gigabyte HBM to the tiny 20 megabyte SRAM.
Which led to the brilliant intervention of tiling.
Right.
Redesigning the loop to keep the intermediate puzzle pieces localized in the SRAM, bypassing the memory wall entirely by accumulating the result on the fly.
And just as we saw the hardware problem, the math struck back. The strict, unyielding requirement of the Softmax operation to prevent floating point overflow threw a massive wrench in the tiling strategy.
You can't compute the whole without seeing the whole.
But you don't have the memory space to see the whole. It is a brilliant, maddening engineering puzzle.
It forces you to rethink everything you know about how an algorithm should be written. And, as we wrap up this deep dive, that is the provocative thought I want to leave you with.
Laid it on us.
If you are a software engineer out there writing code tomorrow, how often do you write logic that is completely blind to the physical memory hierarchy of the hardware it runs on?
Well, I mean, we all rely on compilers to handle that reality for us.
You trust the abstractions. But even if you aren't building giant large language models, could there be a massive flash attention style optimization hiding in your everyday microservices?
That's a great question.
Are you thrashing the CPU cache and choking the silicon with I/O transfers just because big O notation told you the algorithm was optimally designed?
Right.
Sometimes the biggest breakthroughs don't come from changing what the code does, but by fundamentally changing how the code respects the physical space it lives in.
That is incredibly well said and a perfect takeaway. That pure, weightless world of mathematics we learn in school is beautiful, but eventually every algorithm has to live in a physical house. And if you take the time to understand the floor plan of that house, you can engineer some truly magical things. Thank you so much for staying up late nerding out with us on this one. It's been a blast.
Absolutely.
Keep exploring, keep questioning your abstractions, and keep your curiosity sharp. We'll catch you on the next deep dive.